Introduction. Hello everyone, my name is Farhan Rahmani and today we're going to explore the fascinating world of motion through discoveries of Sir Isaac Newton. Newton was an English scientist and mathematician who lived during the 1600s, a time when laws of motion and gravity were largely unknown. He observed the world carefully, from falling apples to the motion of planets, and noticed patterns in how objects moved, resist motion, and interacted with forces. Through careful experimentation and reasoning, he formulated 3 laws of motion that explain how objects behave when at rest, in motion, or interacting with other objects. For this project, I will demonstrate these laws using teacher-based videos in a classroom setting, ensuring that the examples are simple, safe, and use everyday classroom materials. Each law will have 2 separate examples with 1 teacher per law, and all explanations will clearly link the observation to the physics principle using proper technical terms like inertia, acceleration, unbalanced forces, friction, and action-reaction pairs. These demonstrations are designed to be both creative and educational, making the laws of motion easy to observe and understand. So sit back and relax and enjoy this video. Newton's first law, the law of inertia. The first law states that an object at rest stays at rest, and an object in motion stays in motion at a constant velocity unless acted upon in unbalanced force. So let's get straight into example number 1.
Example number 1, object at rest. Mr. Khalidi here will stand right next to the desk holding a stack of textbooks. The teacher will then tap one textbook gently forward while the others remain stationary. So let me give the teacher's instructions. So Mr. Khalidi, stand right next to the desk with 3 to 4 textbooks stacked. Lightly push one forward while keeping the others on your desk. Ensure the push is smooth and visible. Go right ahead. So Mr. Khalidi, do you understand how the example number 1 of an object being at rest relates to the law of Newton's first law?
No, Fardeen, I don't understand. Please explain it to me.
Sure.
So let's go ahead and explain this so that Mr. Khalidi can understand clearly. Newton's first law explanation. Example number 1, an object being at rest. The untouched textbooks remain at rest because no unbalanced forces acts on them. According to Newton's first law, also called the law of inertia, objects resist changes in their state of motion. The tapped textbook moves forward because the teacher applies a horizontal unbalanced force, which overcomes static friction between the textbook that Mr. Khalidi applied force on and the textbook beneath it. As the book slides, kinetic friction acts in the opposite direction of motion, gradually slowing it down until it stops. This example demonstrates how inertia governs objects at rest. They do not move unless a net external force, or rather an unbalanced force, acts upon them. By observing the textbooks, we can see the balance of forces, the effect of friction, and how the unbalanced forces changes the state of motion, linking this simple classroom demonstration directly to Newton's first law. So hopefully Mr. Khalidi understands, and let's get straight into example number 2 of Newton's first laws.
Example number 2, object in motion. Mr. Khalidi here will push a pencil across a desk. The pencil continuously moves after the push ends and gradually comes to a stop. So let me give the teacher's instructions. So Mr. Khalidi, can you push a pencil across the desk with a gentle but visible force? So Mr. Khalidi, do you understand how example number 2 of an object being in motion relates to the first law of Newton's first laws?
No, not quite. Can you please explain it to me, Fardeen?
Sure.
So let's go ahead and explain this so that Mr. Khalidi can understand this example as well. Newton's first law explanation. Example number 2, object in motion. Once the teacher, or rather Mr. Khalidi, stops pushing, the pencil continues moving due to inertia, demonstrating the second part of Newton's first law, being an object in motion remains in motion of a constant velocity unless acted upon an external force, or rather an unbalanced force. In this particular case, kinetic friction between the pencil and the desk opposes the motion, gradually reducing its speed. Air resistance also provides a very small opposing force. The pencil eventually stops because these unbalanced forces, rather friction and air resistance, act on it. This example clearly shows that motion persists until an external force, or rather an unbalanced force, changes it, illustrating how Newton's first law governs real-world motion. So hopefully Mr. Khalidi understands, and let's get into Newton's second law. Newton's second law, the law of force and acceleration, which states that acceleration of an object is directly proportional to the net force applied and inversely proportional to its mass, or rather force equals mass times acceleration. So let's get straight into example number 1 of Newton's second law with the help of the teacher, Miss Subramaniam.
Example number 1, acceleration versus force. Miss Subramaniam will push a single textbook across the desk first with a light force, then with the stronger force. The difference in acceleration will be visible. So, Miss Subramaniam, can you push the textbook gently first, then push the same textbook harder? Keep the desk surface the same, just change the force.
Okay, so this is the first push. Okay, and then this is the second push.
So, Miss Subramaniam, do you understand how example number 1, acceleration versus force, relates to Newton's second law?
No, I don't understand. Can you explain to me?
Sure.
Let's go ahead and explain how this example relates to Newton's second law so that Miss Subratunga can understand. Newton's second law explanation. Example number 1, acceleration versus force. This example demonstrates that acceleration is directly proportional to the net force applied. When the teacher pushes gently, the small applied force produces a smaller acceleration, so the textbook moves slower across the desk. When the teacher pushes harder, the larger applied force produces a larger acceleration, and the textbook moves faster, keeping the mass the same but just increasing force. Friction between the textbook and the desk acts in the opposite direction of motion, slightly reducing acceleration in both cases. By keeping the mass the same, we can clearly see the effect of changing only the force. This is a direct application of Newton's second law, which the formula states acceleration equals force divided by mass. Observing the textbook shows how unbalanced forces, or rather external forces, causes acceleration, and how greater forces results in greater acceleration when mass is constant, since acceleration is directly proportional to the net force. So hopefully Miss Subratunga understands, and let's get straight into the second example.
Example number 2, acceleration versus mass. Miss Subramaniam will push a light textbook and then a heavier stack of textbooks, increasing the mass across the desk with the same force. The heavier stack will accelerate less. So let's see how that works, and let's give the instructions to the teacher. So Miss Subramaniam, can you push a single textbook first, then stack the same textbook, being 2 textbooks in total with the same applied force, just changing the mass?
Okay, so this is the first push. Now I'm adding more mass. This will be the second push with the same force.
So, Miss Subramaniam, do you understand how example number 2, acceleration versus mass, relates to Newton's second law?
No, I don't understand. Can you explain to me?
Sure.
This so that Miss Subratunga can also understand how this example relates to Newton's second law. Newton's second law explanation. Example number 2, acceleration versus mass. This example shows that acceleration is inversely proportional to mass. The single textbook accelerates faster because it has a smaller mass, offering less resistance to motion. The heavier stack accelerates more slowly because its greater mass resists changes in motion. In both cases, friction acts opposite to the direction of motion, slightly reducing acceleration, but the difference in motion is primarily caused by the mass. This clearly demonstrates Newton's second law: acceleration decreases as mass increases if the applied force remains constant. By observing the difference, viewers can see the direct relationship between force, mass, and acceleration in a practical and visual way. So let's get straight into Newton's third law, action and reaction. Newton's third law, action and reaction. For every action, there's an equal and opposite reaction. Forces always come in pairs, equal in magnitude but opposite direction. So let's go ahead and briefly explain this so that we can all understand. If object A applies force onto object B will apply the same exact force but opposite back onto object A. Now let's get straight into example number 1 with one of the best science teachers in Lamoureux Collegiate, Miss Vella, apart from Mr. Wong, of course.
Example number 1, pushing a desk. Miss Vella here will push a small movable classroom desk. As the desk moves forward, the teacher will feel the backward push from the desk. So let me give you the instructions. Miss Vela, can you push a small desk gently across the floor? Observe and feel the slight backward force on the body as well as the desk moving forward. Do you feel that backwards force?
Slightly, yes.
Perfect. So, Miss Vela, do you understand how example number 1, pushing a desk, relates to the third law of Newton's laws?
To be honest, it was never good in physics, so I'd love if you could explain it to me, please.
Okay, perfect.
Let's go ahead and explain this so that Miss Vela can understand clearly how this example relates to Newton's third law, action and reaction. Newton's third law explanation. Example number 1, pushing a desk. When the teacher, or rather Miss Vela, applies a forward force on the desk, which is the action, the desk exerts an equal and opposite force backward on the teacher, or rather Miss Vela, which is the reaction. This is Newton's third law in action. Friction between the desk and floor acts opposite to the desk's motion, slightly slowing it down. Observing this shows that forces always occur in pairs. The push forward on the desk is matched by an equal backward push on the teacher, or rather Miss Vela. This classroom-friendly demonstration makes the law visible and easy to understand, showing the balance of forces in everyday situations. So let's go ahead and get into example number 2 of Newton's third law, or rather action and reaction.
Example number 2, jumping off a chair. Miss Vela here will push down on a chair slightly with her hands while standing on it, then jump gently. So let me give you the instructions. Miss Vela, can you place both hands on the sturdy chair? Push down slightly and then jump off, showing that pushing down produces a reactive force lifting up the body upward. So Miss Vela, do you understand how example number 2, jumping off a chair, relates to Newton's third law, action and reaction?
Actually, Fardeen, no, I do not understand. Can you please explain it to me?
Sure.
Let's go ahead and explain this so that Miss Vela can understand how this example as well relates to Newton's third law, or rather action and reaction. Newton's third law explanation. Example number 2, Miss Vela jumping off a chair. When the teacher, or rather Miss Vela, pushes down on the chair, which is the action, the chair pushes upward with an equal force, which is the reaction. This upward force helps lift the teacher slightly during the jump. Friction between the chair and the floor stabilizes the chair, preventing it from sliding. This simple demonstration clearly shows Newton's third law. Every action has an equal and opposite reaction, and these forces are always simultaneous. Using only classroom materials, this example makes the law visible, tangible, and safe. So hopefully Miss Vela now understands, and let's get into concluding this video. So let's go ahead and conclude this so we can summarize all the points and details in this video. Conclusion. In this project, I demonstrated all 3 of Newton's laws of motion using simple classroom materials and real teachers to make each idea clear and realistic. For the first law, I showed how an object at rest stays at rest, and an object in motion stays in motion unless acted on by an unbalanced force or external force. These examples made inertia easy to see using everyday classroom objects. For the second law, I demonstrated how acceleration changes when we increase force or when we increase mass, showing the direct and inverse relationships in real time. And as for the third law, I used classroom interactions to show action-reaction force pairs that happen instantly and equally whenever one object pushes another. Each example wasn't just explained, it was performed, making the physics visible and easy to understand. These demonstrations helped connect the formulas and laws to real-life motion, friction, force, and interactions. I want to give a genuine thank you to Ms. Vela, Mr. Khalidi, and Ms. Subramaniam, because without their help and willingness to participate in this demonstration, this project wouldn't have been possible. Their involvement made the examples clearer, more engaging, and more creative. Overall, this project shows how Newton's laws are all around us and can be understood through simple demonstrations using nothing more than the classroom and the people in it. Thank you to everyone, and thank you for listening to my presentation.